gets to the fact that I just switched over to a Mac. I'll forget it. I wanted just for a little bit of filler, I had downloaded this National Geographic video of monkeys jumping around and making all sorts of maneuvers, which is was just my way of to comment on the energetics debate that sort of Art and Katie were talking about, and my upshot of it is that I think energy is reasonable currency, but most certainly not what animals are really care about in the wild. And I think there's a sort of a choice between doing what's convenient and doing what's right. And so I think I have to make that decision. Anyhow, I'd like to thank everybody for being here, and thanks for being invited to the conference. I'm going to talk a little bit about unsteady locomotion, and I'm going to change planes a little bit. Most of what we've talked about is in the sagittal plane. I'm going to talk about the horizontal plane a little bit. And I'd like to start with some acknowledgments. Most of what I'm going to talk about is the work of my student, Qiao, who's on the job market for a postdoc, if anybody is interested. Also, undergraduate student who worked with me, Brian Brown. And I'd also like to acknowledge Arizona State University, particularly the School of Life Sciences. Now, I just recently left there, but they've been incredibly gracious and supportive of my transition. So, and all this work was done at Arizona State University. I would like to address what it takes to change direction in the horizontal plane. How do you do a horizontal plane maneuver, like a turn? Turns out that, upwards of 50% of the steps that we take in the real world are turning maneuvers, not counting things like stepping up and stepping down and starting and stopping. So really, the amount of time that we spend just doing steady state walking is less than actually doing these unsteady behaviors. So it's useful to know something about them. What do we have to do, just in the simplest sense, to change our direction and to turn in a horizontal plane? Well, we have to do two things. First, if we're going in an initial movement direction, we have some velocity vector. We have to change that velocity vector to be pointed in a final movement direction, some other direction. And that requires a force impulse to do that, to change our velocity vector. I'm going to call that deflection, just to have to put a term on it. The second thing that we have to do concerns with sort of our body angle. We also have to rotate our body through some angle, which I'll call theta r as opposed to theta d, and that's rotation. To do that requires a torque impulse. Now, a torque impulse and a force impulse aren't the same thing. They don't necessarily have to be the same thing. So there's no guarantee that when we're turning with a leg, if we want to change our movement direction, that automatically our body is going to rotate the right amount. So one question is, how does rotation, body rotation, match movement change or movement direction change or deflection during turning? And to address this, what I did was just came up with a very, very simple mathematical model or description of the problem. Now, this model is not based on any sort of physical principle like a slip model. It's based on some sort of reasonable approximations to the physics of the system and how it works. But it's not conservative. It doesn't make efforts to be constitutive. And I'm not going to go into detail about what it is or what the assumptions are, but really what it does is it expresses the idea that if you turn with a leg, how much body rotation you get relative to how much movement deflection you get. And it turns out that you can come up with this fairly simple algebraic relationship involving parameters that are important to me as a biologist and things I can think about and measure, such as mass, speed, step period, and yaw moment of inertia. So these are parameters of the model, and then so that's the first term, which is very, very simple, and then there's this second term, which is essentially a position term, and that involves also the anterior posterior foot placement. But what this very, very simple mathematical relationship in bodies is, if you're going to change your movement direction with a leg, how much body rotation do you get based on all these parameters? I call this our leg effectiveness number. And you can sort of see that if the value is 1, it means rotation matches deflection. It means that at the end of a step, of a turning step, you're actually pointed in the direction that you're going. I hypothesize that that's something that we'd like to do. And so if your leg effectiveness number is about 1, then your leg is pretty effective. So, one approach, the first thing I did is try to estimate leg effectiveness for humans. So I just went into the literature, actually, and got some literature values for these things. And what I found was that during walking, it was about 1.8 to 2.3, and running, it's about 2 to 4. Say, so it's about, roughly 2 to 4 for humans. Oh, what does this mean? Because this is higher than 1, it means that, which is greater, rotation or deflection? Rotation. Yeah, it means that over-rotation is potentially a problem for humans. You get too much rotation for a given amount of deflection, potentially. So I'm going to have to try to test this. Oh, sorry. What can we do if we're confronted with this situation? Well, there's a simple answer, is that we can generate braking forces, decelerating forces. We have a lateral foot placement, gives us a lever arm, and if we just generate a braking force, we can control our rotation and prevent over-rotation using a braking force. So a braking force looks something like this. If we have our normal fore-aft forces, our normal fore-aft forces associated with running. It's a sinusoidal type thing. A braking force is just linearly superimposed on this fore-aft force, and you end up with a ground reaction force that looks something like this black line. And so you can decompose that. You can actually decompose these the ground reaction force into a braking force and into a sinusoidal force associated with the slip. So there's potential that this is superimposed on the slip. So I went about trying to measure this, and again, it looks like my videos are not working. Okay, well, apologies for that. The videos are not working, but what you'll see, what's that? Okay, the demo is that they're very, very simple maneuvers. I really wanted to show the ostrich video because it's beautiful, but I looked at cutting turns where people would come up and then just do a single cutting maneuver like that. These are not circle running, but single cuts. So what did I find? Well, if I just used a simple model to make a prediction and compared it to the braking forces that I measured, what I found was that, so I did this simple experiment with both humans and ostriches, I should have mentioned, that both humans and ostriches, for both humans and ostriches, I could predict fairly well the braking forces actually used by the animal, even with this very, very simple model. So I ended up with fitting regressions to this. The slopes to both of these regressions were roughly 1, and the R-squareds were about 0.7. Now, you can notice a couple of things about this. One is that, one thing that's interesting is that these are roughly the same turns, and they're roughly the same speed. So all the trials, essentially the target was similar, but there's high variance. And so individual turns are performed in different ways on a trial-by-trial basis. So there's a lot of covariance among these model parameters, but individual turns are quite different. The other thing that you notice is, what are ostrich braking forces relative to humans? Are they less or more? Smaller? They're smaller. They're closer to 0. So ostriches use far lower braking forces than humans did. So that's interesting. So a few observations from this. A very simple model relating morphology and behavior was able to make predictions about the forces actually used during these maneuvers. There's substantial variance, but this variance is consistent with the control of body orientation for both animals. the fact that the model worked suggests that, the underlying hypothesis is reasonable. And ostriches shows a smaller average, lower average braking forces. Well, why is this? Well, it turns out that ostriches and humans differ in mass, but actually, size-wise, they're not so different. I looked at juvenile ostriches, not gigantic ostriches, but ostriches that were more similar in size to humans. Turns out that the differences among ostriches were not due to a single parameter. They were due to small changes in many different parameters, like lateral foot placement, stance periods, and this ratio of mass to inertia. And fore-aft foot placement. So what this suggested is that there wasn't a single parameter that was different between these animals, but multiple parameters changing simultaneously. So I want to do this, just talk about this very, very quickly, that I decided to do a second experiment and ask the question, well, can we make a human more like an ostrich? And see what happens. Is the compensation, does the model break? So what we did is we added weights to humans on this backpack and just changed the moment of inertia. We just toggled one parameter of the model. And our prediction would be increasing moment of inertia 2.2 to 4-fold would decrease the braking forces down to ostrich levels. Well, the video's not going to work, but I'll show you the results. The results were that the predicted, the leg effectiveness goes down to about 1. So the model says that there should be lower braking forces. The model says that there should be lower braking forces, and the predicted braking forces of the model. But actually, humans don't use lower braking forces, so the model breaks. Now that's, sort of crushing initially, but ultimately interesting. So humans become like ostriches, that decreases the predicted braking forces, but the measured braking forces aren't different. So why didn't they change among these parameters? Well, it turns out that for most parameters I looked at, there was no change whatsoever on average among conditions. And again, similar to the comparison of humans and ostriches, it wasn't a single parameter that changed among inertia conditions, but a bunch of different parameters. And it turned out that initial rotational velocity was the most important one. If you put that back into the model, you're able to recapture the predictions. So just some very quick conclusions. Very simple models can describe maneuverability. Every maneuver involves slightly different combinations of variables to achieve the goal. This is very consistent with what Young-Hee talked about the other day, where you have these covariants among variables that to achieve a common task goal. And I've expressed this sort of in another plane. Compensations involve minor changes to several variables, and greater inertia increases permissiveness. I'm not going to talk about this, but we can talk about it after if anybody's interested. And increases the space of behavioral options for maneuvers. So thank you very much.
Standing on the stage, show what is the, because there are lots of ways you can turn and lots of ways you can deflect sideways, or at least a few.
Yeah.
Can you show what is your assumed form of the maneuver for turning it?
So my assumed form is a cutting turn. And what I assume, the assumptions underlying the model are that roughly that there are not torques. So one thing is that I assume, and you don't measure that you do it using torques at the foot. And I also assume that you don't use, and people don't use a lot of body roll. So it seems like the body is rolling when you look at people turning, but when you actually look at the data, it's deceptive. People do increase their lateral foot placement a little bit, so that's in the model. And so they stick their foot out laterally a little bit, and it makes it look like their body, to our eyes, is leaning over. But actually, if you look at the trunk, there's not very much lean at all.
Show what you can slow mo to do walking instead of running.
Yeah, well, walking might be completely different. So that's an issue.
What you're talking about.
Yeah.
So which is the side?
So it's the foot that is in stance while you're changing direction. So that's the foot that I'm modeling.
And why is it that there's a fixed ratio between the torque and the sideways force? And what's the braking force you're talking about?
So there's not, so the braking force would be a decelerating force. in the initial movement direction. And so, but when you generate the force to try to move your laterally, because your leg is not directly lateral to your center of mass, you end up with a torque that causes body rotation. So the question is does that torque rotate you the right amount? And it could even, potentially rotate you, the opposite way.
I think I can't get this fast enough, so I'm going to give up.
Okay.
I think
Wow.
we're unfortunately out of time, so
Okay.
we'll have to.
If I confused Andy,
discuss during the coffee
that's
break.
something. Okay. Well, thank you very much. Appreciate it.